You mean you don't know everything there is to know about power series now?
Binomial x minus a is being raised to the n power. How can we assess whether this kind of power series is convergent or divergent? Sometimes we will use the ratio test. Take something like the quantity x minus 3 raised to the n power over n. Remembering the ratio test from the previous tutorial, let's change n into n plus 1, and then take the regular version and flip it to bring it up here. To simplify, x minus 3 raised to the n plus 1 can become x minus 3 raised to the n times x minus 3 raised to the 1. This more complicated term then cancels, leaving us with x minus 3 times n over n plus 1. Now let's divide this fraction by n to get 1 over the quantity 1 plus 1 over n. As these are all positive, we can pull them out of the absolute value brackets, leaving just x minus 3 in there. Now bringing n up to infinity, this whole part just becomes 1, leaving us with the absolute value of x minus 3. In order to be convergent, this has to be less than 1. So given the absolute value, we know that x minus 3 must be less than 1 and greater than negative 1. Adding 3 throughout, we get x as being between 2 and 4. So those are the values for which the series converges.
Remember doing that? You had a couple homework questions where you had to do that.
In general, there is a theorem that summarizes the 3 possibilities that can describe a power series in this form, depending on the precise series. One possibility is that the series converges when x equals a. A second possibility is that the series converges for any value of x. And lastly, there could be some positive number r, such that if the absolute value of x minus a is less than r, the series will converge, and if greater than r, the series will diverge, just like the example we just completed. In this third case, that number r is called the radius of convergence for that power series. The first 2 cases also involve a radius of convergence. It is simply that for the first case, the radius of convergence is 0, as there is only one value that will allow for convergence. And for the second case, the radius of convergence is infinite, as any value will allow for convergence. We can also describe the interval of convergence as the interval describing all the values of x for which the series converges. Let's try an example and see how this applies. Take x to the n over n factorial. What can we do with this? Let's try the ratio test. We get x to the n plus 1 over n plus 1 factorial. And then, given the original series in the denominator, we just multiply by the reciprocal, or n factorial over x to the n. We've simplified something like this a couple times by now, so let's change n plus 1 factorial into n plus 1 times n factorial. And let's change x to the n plus 1 into x to the n times x to the 1. Most of this cancels out, and we are left with x over n plus 1. Finding the limit as n approaches infinity, we see that we will get 0 no matter what the value for x. This means that the radius of convergence is infinity, and the interval of convergence is negative infinity to positive infinity. This fits the second possibility from that theorem, which tells us that this series is always convergent. That covers the basics regarding power series, so let's check comprehension.
We're not gonna do that. Okay, he also had the infinity and negative infinity backwards.
I saw that.
That bugged me. I didn't notice that before. Come on, Professor Dave. You're better than that.
I'm sure no one else was.
Okay. Well, someone wants him to fix their life. So if you're relying on Professor Dave to fix your life.
Negative, positive.
What's that?
My therapist.
Okay, so I'm gonna kind of restate everything that he was just talking about, but I wanted you guys to see just an intro. I think, at least for me, I know when I was learning stuff, it's helpful to like see it. You don't have to write anything, then see it a second time and do the problems. That's why I show those. I don't know if it helps or not, but okay. So open up the notes and we're gonna dive into this whole idea of power series and what he was talking about. On this very first page of notes, there's really nothing to write. It's just kind of a lot of information, and I'll summarize. I'm not going to read through everything, but I'm going to kind of summarize this. But notice how we can say e to the x, this function right here, is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus ... plus x to the nth over n factorial plus ... Like it goes on forever. Notice we're saying e to the x equals that infinite series. It's equal to that. And that's the whole reason these series are a thing. What is not on this note outline, the formatting didn't come through. Like technically there should be ... here between those plus signs, and you should have plus ... going on forever. Like those things actually need to be there. If you're taking your free response questions and they ask you to write the infinite series and you don't put plus ... on the end, you actually don't get full credit. So those, I mentioned last time, those ellipses do matter. I'm not sharing this screen to you guys at home. Am I?
Now it's raining, Mr. G.
It's raining?
You can see it now.
Oh, yeah. Let's just admire the rain.
Just listen to it.
Blame it on the rain. Yeah. What's that?
I just feel bad for anybody who's watching this lesson video that just watched this. Very bad. Very good.
Yeah.
Just in 5 years from now. 'cause when you're still-
I'll have these on Canvas. I mean, these are always going to be on Canvas. Always. Like, I don't anticipate ever not having them on there. You know? I don't ever plan on like showing them as a lesson, but if I'm sick or my kid is sick that day, it's, you know, the lessons are there. That's the whole point.
These are mortal
So,
lives.
you know, you guys that are on Zoom, sometimes you could see your faces. You'll be it like.
I was watching one yesterday, and Holly was the only one who had hers on.
Yeah. And she was not lying about
Not.
the
No,
camera being
I
messed up.
saw.
Yeah.
I
Okay.
was like waiting for you to say something.
I tried to wait on that last one.
Yeah, I know.
It happened again at the end, but you could still see the problem. So I decided to just kind of.
So what happened in block 7 that day? We were doing the lesson. I was starting the lesson on discs and washers, and they said it was messed up. So I quit the Elmo. I turned it back on. Usually that helps. It didn't. I tried again, turned it back on. They still couldn't figure it out, and I just told them to leave. I had recorded Monday's lesson for AB, and I said, just leave and watch that video. So it was helpful that it was on there. Did they watch it? I don't know. It was a nice day out. I would have gone outside. But hopefully they have watched it coming into today. That's the hope. Okay, so in the video, he talked about a couple of things. He talked about the radius of convergence, and he talked about the interval of convergence. And those are going to be the two things we're after today. We're basically trying to figure out for what x values is this actually true? Like if we define a function, f of x, as an infinite series, for what values of x is that true? It's not always true for just any value of x. We have to figure out for what values of x does that series actually converge to a value. So that's us finding the interval of convergence, which we'll talk about at the very end. For the radius of convergence, I want you guys to see this. So there are three things that can happen. The radius of convergence could be 0. What that means is the series only converges at one single point, at C. Like if I plug C in for x right here, then we would have C minus C and we would get 0. So it's always going to converge at whatever that C value is. We could also have an interval of convergence, which we are going to talk about, but basically, you know how he said this one converges from -2 to 4 or whatever. I don't know what the values were. That's your interval of convergence. The radius of convergence is half of that interval length. Like if I'm going to put numbers here that mimic what the video was, let's say that this series converges from -2 to 4. Well, then your radius of convergence is going to be 3 because that interval is 6 units long. The radius of convergence is always half of that interval. So from that, where you're centered around to one of your outer interval values. So the radius is always half of your interval. Okay. The last thing that can happen is the series can converge for all values of x, in which case the radius would be infinity, meaning it just converges for everything. You would have to write your interval correctly from -infinity to infinity, not the way he did it. I don't know why he did it that way. Anyway, so whatever those values of x are that make the series converge, that's our domain. Okay. The rest of the lesson is kind of finding the radius of convergence, the interval of convergence, and just practicing the ratio test over and over and over again, and working on the algebra, seeing things that can happen. So for a power series centered at C, one of the following is true. The series converges only at C itself, so the radius would be 0. There exists a real number r greater than 0, such that the series converges absolutely for this right here and diverges for anything greater than r. This is pretty much what we're going to be focusing on a lot today, this right here. We're going to be trying to get our ratio test to eventually look like this right here. We want to do our ratio test. We want to take the limit as n goes to infinity. And this, a lot of times, is what's going to happen. And whatever this value is right here, that's our radius of convergence, whatever that number is, okay? Or the series converges absolutely for all x, the radius would be infinity, okay? So we're going to go through and kind of practice doing these things. It says find the radius of convergence for each power series. So the question is not asking for what values of x do these series converge. It's just saying what is the radius of convergence? And I actually want to do b first. I want to do b first. If you guys are okay with that. You guys okay with that?
I guess.
Okay. So we are going to do the ratio test. Anytime we're talking about the radius of convergence or the interval of convergence, that is the ratio test that we're going to be doing. Okay. If you guys at home see the Elmo is messing up, please shout out. I will believe you. Remember, the ratio test says this. We take the limit as n goes to infinity of the absolute value of the next term over the previous term. That's what we do. That's kind of our procedure. And for the series to converge, this has to be less than 1. We want that limit to be less than 1. We're trying to figure out what x values make that happen. As we go through this, one important thing to understand, and you guys practiced this last chapter, so this will probably make some sense, but we're going to treat x like a constant. Like when we do our limit, it's as n goes to infinity, like n is the variable that we're working with, but we're going to treat x like it's a constant throughout our work. Treat x like a constant. All right, so let's go into the first example. We're going to do b, okay? So I want to find the radius of convergence. So I'm going to start with the limit as n goes to infinity of the absolute value. And I'm going to take anywhere I see an n, I'm going to put n plus 1 in. I'm talking about the next term. So it would be 3 quantity x minus 2 to the n plus 1. And then it's divided by that sequence inside of sigma, but we multiply by the reciprocal. So times 1 over 3 times the quantity x minus 2 to the n. Before we say like this is less than 1, we don't know if that's true. We need to actually do all our algebra work now and figure out what this equals. So I'm not going to put less than 1 right now. I want to clean all this up. So the 3's cancel. X minus 2 to the n plus 1 over x minus 2 to the n is just x minus 2. And he showed that in the video. If you remember why, x minus 2 to the n plus 1 is the same as x minus 2 times x minus 2 to the n. Like these two expressions are equivalent to each other. So the x minus 2's to the n's cancel. And so we just have the limit as n goes to infinity of the absolute value of x minus 2. Now, the nice thing on this one is there are no n's to even think about. This is like in the summer. You guys remember doing the limit chapter way back when in the summer before school started? And one of the limit properties said this: if you take the limit as like x approaches 3 of 5, if there is no variable in here, then this part doesn't even matter. It just equals 5. And that's what's happening here. Since there is no n inside of here, then this limit just equals the absolute value of x minus 2. I stress that because some students will plug infinity in for x, not understanding like we're dealing with n's there. Okay, so that's what that limit equals. I still would not put less than 1 here because we don't know if that's a true statement. What we're trying to figure out, this series converges when x minus 2 is less than 1. So the series converges when this happens. Our goal for the radius of convergence is to get to a form that looks like this. The absolute value of x minus c is less than some number. That number is your radius of convergence. What that means for this problem, 1 is the radius of convergence. That is r. So the radius of convergence is r equals 1. I stress getting to that form because what will happen, I think it happens on the homework a few times. I don't know if it happens on these notes or not, but what's going to happen is this. Sometimes you'll be doing these problems and you'll get to a place where it's like the absolute value of x minus 1 over 3 is less than 1. Like you'll get here, well, r is not 1 in this case. We would have to multiply by 3 and make it look like that form. And so the radius on that would actually be 3. So we're trying to make it look like the absolute value of x minus something is less than a number. That number is your radius. And that's all we're finding on this problem. We're not finding the actual values. We're done. So the radius of convergence is 1. I want you guys to try A, please. And thank you. A triple dog dare you. It's not raining as hard. Huh? Hmm.
Nobody's gonna come in.
Any rain? All right. Here's your work for that. Hopefully you got r equals 0. So we set up the ratio test. N plus 1 factorial over n factorial is just n plus 1. We can cancel out x to the n, so we're left with x. Here's a little trick. Since x is a constant, we're treating x like a constant. If you have a constant inside of a limit expression, you can actually pull it out in front of the limit. That's just a limit property from way back when. So if we're treating x like it's a constant, we can actually pull the absolute value of x out in front here and just evaluate this limit right there. Regardless, it's infinity. We're trying to figure out, when will this limit be less than 1? Well, that limit is infinity. It will never be less than 1. It will never be less than 1. But these things will always converge for at least one value. And that would be at 0 when x is 0. Because it's when x equals c, and c in this case is 0. But this is after the radius. The radius is 0. So your radius is either 0, infinity, or a number. Those are the only 3 things that can happen. That make sense? Yes, no, maybe so. Ho, ho, ho. Okay. All right. Next one. Kind of a fun one. Let's ratio test this bad boy. I'm going to ratio test you. Limit as n goes to infinity of the absolute value. We're going to plug n plus 1 in for all those n's. Be careful there. So notice where those n's are. We replace the n with n plus 1, but all the other stuff still stays there. We'll clean that up here in a second. So the nice thing with the ratio test is anytime you have that -1, that alternating component, the absolute value just makes that go away. So that's nice. And then we're going to clean this up a little bit. So we get the limit as n goes to infinity of the absolute value. Well, the -1 to the n plus 1 and the -1 to the n, those just become positive ones. Those are done. Distribute the 2 inside of here. So let's see. This is 2n plus 2 plus 1. So this is x to the 2n plus 3. On top is 2n plus 1 factorial. On bottom, let's see, 2n plus 2 plus 1, so 2n plus 3 factorial. X to the 2n plus 1. Okay. So now you got to figure out how to cancel out those factorials. Does anybody know what 2n plus 3 factorial is the same as? Like how we can get that to cancel out with 2n plus 1 factorial? X to the 2n. No, not the x's, the factorials.
Oh,
You were right on the x's though. Anybody know how we can like expand 2n plus 3 factorial? Times. So close. No. She said 2n plus 1 factorial times 2n plus 2 times 2n plus 3. So think of 2n plus 3 being like the biggest term, right? So we got to start there. So 2n plus 3 factorial, you don't have to write this, but just to show you how this breaks down. So 2n plus 3 factorial is equal to 2n plus 3. So that's like the biggest number. Like if it was 7 factorial, 7 would be the first number. Well, the one number right below that is 2n plus 2. And then the number right below that is 2n plus 1. And we can just put factorial because that's the thing that we're trying to cancel out on top. I remember I had a math class. It might have been calc too, but I remember doing a lot of factorial work. And I liked it. I don't know why. I found it very satisfying. I think it was discrete math. There's a lot of probability and combinations and permutations. And I remember factorial coming up a lot. I enjoyed it. But I'm weird. Okay. So this equals the limit as n goes to infinity of the that's the worst infinity ever, of the absolute value. Well, we're going to get x squared on top. And the reason we're going to get x squared on top is, think about your exponent rules. If you're dividing these two x's, you would keep the x and you would subtract the exponents, right? Whatever you get when you subtract your exponents, that would be the new exponent. So 2n plus 3 minus 2n plus 1 is just x squared. So you're keeping the base, you're subtracting the exponents. And that's going to be over, well, the 2n plus 1 factorials cancel. So it's over 2n plus 3 times 2n plus 2. If we're treating x like a constant and we're making that denominator infinitely large, then we basically have some constant over infinity, meaning this equals 0. What that means is this is always less than 1. This series converges for all x values. That means the radius of convergence equals 0, or is infinity. Sorry. Hopefully that didn't screw you up. The radius is infinity. This series will converge for all values of x. Lastly, the interval of convergence. So they call these problems FRQ cash cows. You know how in AB, we did those problems where they gave a differential equation and you had to separate the variables, and then you had to integrate both sides, and then you had to find C, and then you had to solve for Y. You guys remember solving differential equations? Like those problems on FRQs are usually like 5 points. You get a point for separating, you get a point for integrating each side correctly, that's 3. You get a point for finding C, and then you get a point for finding what Y equals. That's kind of what happens on these. These problems on your AP test are typically going to be worth 5 points. I'll kind of show you where those points get doled out, but these are big time problems. So we're now trying to figure out for what values of x do these series converge. So what we need to do on this one is the same thing we just did on the previous 3 examples, same exact process, but now when we get to that inequality at the end, we have to solve that inequality to find the interval. But not only that, we also need to see, so the ratio test is inconclusive when the limit equals 1. Like at the endpoints, it's inconclusive. So we then actually need to plug each endpoint in to our series and see if the series actually converges at the endpoints. That's where all these points get doled out. Like doing the ratio test correctly, getting to the step where you have, the absolute value of x minus 1 is less than 4, whatever, then finding your interval and then testing each endpoint. These are like 5-point problems. Okay, so let's do it. We're going to take the limit as n goes to infinity of the absolute value of x to the n plus 1 over n plus 1 times the reciprocal, so n over x to the n. So we could do some n over n plus 1. We can't simplify that. So what do we get? We get the limit of the absolute value as n goes to infinity of the absolute value of x and then times n over n plus 1. So what happens on this, since x is like a constant, I can pull the absolute value of x out in front like this. And now we're just analyzing the limit of n over n plus 1 as n goes to infinity. What does this limit equal? It's just 1. Those are your horizontal asymptote rules. That just equals 1. That limit is 1, which means this whole thing equals the absolute value of x. What they say is don't write less than 1. You go to another line and then kind of write out so it converges when the absolute value of x is less than 1. So if the question said, what is the radius of convergence? That's 1. If that was the question, it's 1. Okay, r equals 1. But this question is asking for the interval of convergence. So this is where we have that absolute value inequality, and we have to solve it. When this happens, we take this number, we put it on the other side, but make it negative, and the absolute value goes away. So when you have that absolute value expression less than 1 or less than whatever it is, pull the opposite of that number on the other side. So here's what we know so far. We know this series will converge for any value between -1 and 1. What we don't know is what will happen when x is -1 and what will happen when x is 1. What happens at the endpoints? Typically what will happen, I don't know what's about to happen on this one. I haven't looked ahead at my key. But on an AP test, typically what will happen is you'll plug in one of your endpoints and it'll be like an alternating harmonic series which converges, and the other one will be the harmonic series which diverges. Typically one will make the series converge and one won't, and that's them assessing, do you actually understand these series convergence tests? So we need to check the endpoints. So big asterisk, don't just stop here, check the endpoints. And when I say check the endpoints, we are literally taking each endpoint and plugging them in for x in the series. And then it's like we're going back to last chapter and thinking about our convergence tests. Like, does the series actually converge? So first, let's check -1. So if I plug -1 in for x in the series, we would have the summation from n equals 1 to infinity of -1 to the n over n. Does that converge or diverge? Converges. The harmonic series diverges. The alternating harmonic series, which this is, converges. So this converges because it's the alternating harmonic series. So we know -1 is going to be included in our interval. We need to check 1. So we're going to plug 1 in for x, and we get 1 to the n over n. So 1 over n. That is the harmonic series, so that will diverge. Usually on these problems, they've said like, you've done enough that you should get to, when you do this, like you shouldn't then have to run through a series test like you've had to do with like the limit comparison test. Like you've done enough work that when you get here, you should be at a point where you can look at it and know you can state converges or diverges. You're not going to have to do a lot more work once you check that. They just want to see a couple of things. They want to see, do you know you need to check the endpoints? And then do you know whether those series converge or diverge over here? Okay. So our interval of convergence is -1 to 1. And so bracket on the -1, parenthesis on the 1. -1 is included in the interval, 1 is not. What do you think? if you know how to do the ratio test, you're basically getting 3 out of the 5 points already, even if you forget about checking the endpoints. I'm gonna have you guys try C. I'm gonna have you try C. Find the interval of convergence. Why did it go haywire? There we go. How'd you guys' physics test go the other day? That was around the same time as this one. Is it okay?
I've heard.
It's the highest scoring test of the year.
For me.
Oh, for you?
Yeah, like
Not for you?
Yeah, several.
Not for you? Like with the curve, is it fine?
It's like you end up okay. But it's-
Yeah.
This is the lowest period I've ever
Little
been.
sting. You guys have so much testing for your AP physics test. You're talking about last time. You have tests all day till 5 p.m. From 9 to 5, because you have 2 physics tests on the same day, right?
Yeah, they're short tests.
Oh, they are. They're not. It's like this test is like almost 4 hours.
Yeah, it's like 2 half tests.
Oh,
I don't think that's the one that I got.
I don't know, once we're at 12.
Yeah.
It's the first one, at 12, not 8.
Yeah.
they're starting the testing at 9.
But I have a second test started.
Is it like a weird, like,
Nope.
on the chart, like, it has like the 9 o'clock and has like a 4-hour thing or whatever, so there's a weird time. for physics to start early.
Well, that's good then. All right, here's what I got for that one. I got -1 to 1 inclusive, including -1 and 1. That is. So this was my work. When I went through the ratio test, again, I got the absolute value of x. To converge, I set that less than 1. That gave me my interval without including the endpoints yet. And this is what I was talking about for like, I think if you plug -1 in, it's not the alternating harmonic series. It's actually even better, a more convergent series than that. And so you can't say the alternating harmonic series, but I just have said it converges by the alternating series test. And I think if you just say it converges, you'll be safe on the AP test. You've done enough work up to that point. I don't think you need to run through your test. And then at 1, you get 1 over n squared. So that series converges. So -1 and 1 both are included. Make sense? The next one's fairly tough, so I wanted to do that one for you guys. So our last one. All right, last one. So we're gonna start it the same way, but just some of the manipulations within the problem get kind of fun. All right, so we have the limit as n goes to infinity of the absolute value of -1 to the n plus 1 times x plus 1 to the n plus 1 over 2 to the n plus 1. So let's see, 2 to the n plus 1 on bottom is the same as 2 to the n times 2. So those 2 to the n's will cancel. You'll have x plus 1 to the n times x plus 1. So you'll have x plus 1 on top and 2 on bottom. Is that right? All the n stuff goes away. I do that right? I'll take that as gospel. And then since there's no n's in there, the limit as n goes to infinity of this fraction is just this fraction. So that's what that limit yields. This series converges when that is less than 1. So the series converges when the absolute value of x plus 1 over 2 is less than 1. So this is what I was talking about on the previous page. If this question said, what is the radius of convergence? It's 2, not 1. Because we would be able to multiply 2 to the other side. The other thing you could do is find the interval of convergence, like figure out how far that is and divide it in half. Like that's another way you can find the radius. But this is going to be the absolute value of x plus 1 is less than 2. So r is 2. The radius is 2. And now I need to solve this inequality. So I'm going to pull negative 2 off to the left is less than x plus 1, less than 2. And then subtract 1 from the middle and then both edges. So I know this series will converge for all x values between -3 and 1. I know that. Now I need to see, will it converge at -3? Will it converge at 1? So I'm going to plug those numbers in. So at x equals 3, we have from n equals 0 to infinity of negative, oh, it's -3, by the way. My bad. So we have -1 to the n, and then that's going to be -2 to the n over 2 to the n. Anybody know what -1 to the n times -2 to the n equals? What'd you say? Huh? 2 to the n.
Oh.
Be 2 to the n. So -1 to the n times -2 to the n is just 2 to the n. So we have 2 to the n over 2 to the n. Those cancel. That's just 1. Bless you. Was that a sneeze? Okay, I can tell that a sneeze or a cough. Bless you. So we have the series from n equals 0 to infinity of 1. That just means we're adding 1 forever. That diverges. We got to check 1. So -1 to the n times 2 to the n over 2 to the n. This one, those 2 to the n's just cancel. And so if you would like expand this out, this means you're adding 1, -1, +1, -1, +1, just all oscillating. It's never converging to an actual number. So this also diverges. So neither endpoint worked. So our interval of convergence is just -3 to 1. Whew. Good stuff. Good stuff. So I'm done. I was watching this Professor Dave Explains video, and this morning I was like, what's the big difference between a Taylor series and a power series? These are all power series. And technically Taylor series, we haven't actually talked about yet, but that's the culmination of the course. A Taylor series is a power series. And so next class, we're just doing some AP examples, but I wanted to, as I was watching his video, the next one was like Taylor series. And I put a link to it at the bottom of our Canvas page. I didn't know how long this lesson would take. I'm just going to show it now, leading into next class. It's a real short video again, but I'm going to show it and then we'll be done. Okay. So I had it queued up right here. AirPlay, stop share, switch source. Was it? I heard it. Oh, that makes sense. I heard in Japan they're opening up Super Mario World soon. Yeah, like Disney or Universal or something. Looks cool. One of the rides is like Mario Kart. Right. All right, Professor Dave, what do you have in store for us today?
Professor Dave, let's learn about Taylor and Maclaurin series.
He knows a lot of all kinds of stuff. Professor Dave explains.
In the previous tutorial, we talked about power series. These were series in the following form: C sub n times x to the n from 0 to infinity. We mentioned that the sum of a power series can be represented by a function, with terms involving each power of x all the way to infinity. But we may want to know something about all of these coefficients. Now that we understand differentiation, we are ready to expand our understanding of this kind of series. So let's talk about this now. Say we are looking at this power expansion, the series C sub n times the quantity x minus a raised to the n power. We can describe this with a function, but we may want to solve for these coefficients. It actually won't be as tricky as you think, given the difference x minus a in each of these terms. If we find f of a, all of these binomials become 0, and therefore all of these terms become equal to 0, except for the first coefficient here, c0. So f of a equals c0. With the first coefficient down, how do we get the next one? This is where differentiation comes into play. Let's say we take the derivative of this function. c0 will go away, since the derivative of any constant is 0. Then for the second term, x minus a will go away, leaving c1. To be clear, if we were to distribute before taking the derivative, we would get c1x minus c1a. And since c1a is just a number, that will go away, and c1x will become c1. For the other terms, we will use the chain rule. Starting with this one, the 2 comes down here, leaving an exponent of 1, and then we multiply by the derivative of what's inside, which will just be 1. So we are left with 2c2 times the quantity x minus a. The second part of the chain rule will always be 1 for the rest of these terms, so we can just do the part with the exponent. 3 comes down here, and the exponent becomes 2. 4 comes down here, and the exponent becomes 3. Now with this expression, which represents the first derivative of the function, if we plug in a, all of these terms will disappear, just like when we plugged a into the original function. The only thing left is c1. So f prime of a, or the derivative of f evaluated at a, equals c1. Let's go back to the expression for the first derivative and take the derivative again. c1 goes away, and this term becomes 2c2. Then we have 2 times 3, or 6c3 times the quantity x minus a. This next coefficient becomes 12, and so forth. Again, plugging in a for x will isolate the 2c2 term. So f double prime of a equals 2c2, or c2 equals f double prime of a over 2. By now, we might see a pattern. Taking the third derivative and plugging in a will give us f triple prime of a equals 6c3. Or c3 equals f triple prime of a over 6, which can also be expressed as 3 factorial. Inputting a into the fourth derivative of f will give us 24c4, meaning that c4 equals the fourth derivative of f over 4 factorial. We can therefore set up an expression to find the nth coefficient of the series. C sub n equals the nth derivative of f evaluated at a divided by n factorial. This works for all the terms, even the first, if we understand that the 0th derivative of a function is simply the function itself, and that 0 factorial equals 1. So to summarize, for the function given by the sum of c sub n times the quantity x minus a to the n power, where the absolute value of x minus a is less than the radius of convergence for the series, the coefficients of the function are given by this formula. If we then generate a new function of the same form, but substitute this formula in for c sub n, such that the terms in the series look like this, we have just generated the Taylor series of the function f at a, which can also be described as f about a, or f centered at a. So a Taylor series is a type of power series, but with the coefficients defined like so. Now that we understand what a Taylor series is, let's also define a special case. For the same type of function, but where a equals 0, this binomial becomes simply x to the n. And everywhere we were plugging in a, we simply plug in 0. So we get f of 0 plus f prime of 0 over 1 factorial times x, plus f double prime of 0 over 2 factorial times x squared, and so forth. This is a special kind of Taylor series called a Maclaurin series. This is a Taylor series where the expansion is about the point x equals 0. So we should definitely be aware of these definitions for a Taylor series and Maclaurin series, because we are going to apply these expansions to specific functions. Take, for example, e to the x. Let's find the Maclaurin series that represents the function f of x equals e to the x. That will be the nth derivative of e to the x evaluated at 0 over n factorial times x to the n. Well, what do we know about e to the x? The derivative of e to the x is e to the x. So no matter what derivative we are looking at, we just have e to the x. Also, we are plugging in 0 every time, and anything to the 0 power is 1. That means any derivative of this function evaluated at 0 will give us 1. So this entire term can just go away, leaving us with x to the n over n factorial. We can therefore quite easily begin writing out the series with x to the 0 over 0 factorial, or simply 1, plus x to the 1 over 1 factorial, plus x squared over 2 factorial, and so forth. This should look very familiar, as we have just derived a form for e to the x that we utilized earlier in this calculus series. That form was actually the Maclaurin series for the function. Let's make sure we can find the radius of convergence for this function. That will require the ratio test.
So that was all. Just the Taylor series is a power series, but taking its derivative, nth derivative over n factorial. We'll practice next time. So the main thing is understanding how to do FRQs. So you had one last night for homework. Tonight you don't. You have some book problems, practicing the ratio test and stuff. I think next class we start with a warm-up, Taylor FRQ, and your homework next time is a Taylor FRQ. And then Wednesday for e-learning next week, you have 2 or 3 Taylor FRQs. So between last night's homework and next Wednesday, you'll have seen like 5 or 6 of the most recent Taylor series FRQs. If you could do those 5 or 6 FRQs, then nothing will surprise you at that point. So, and then we'll have our review day next Friday and then a test. That's our plan before spring break. Then we're gonna review. I don't know what we're gonna do yet for review. I haven't thought past spring break. What do you guys want to do for review? Just a bunch of like practice problems, FRQs, multiple choice practice, AB, some AB review stuff.
A lot of baby.
A lot of AB review stuff. You might be surprised how much you actually know about AB calculus. I know it feels like a long time ago, but AB calculus, guys, was just like finding derivatives with chain rule and product rule and quotient rule. U substitution. What else was in it?
Mr. Giordano, you might be surprised how little of AB I know.
I don't think that's true. I think you'll remember a lot more. Absolute maxes and mins, relative maxes and mins, inflection points. Hey, that about sums it up, guys. That was AB, like those things I just said. There's not a lot in AB. So I'm not saying you guys know it all, but you might be surprised. Okay, so you guys at home are free to go. Peace out. Quit the Zoom.